So, thank you for coming. Last day, well, Thursday night reInvent. I definitely appreciate all of you coming. My name is Jason Tatro. I'm an associate director slash architect slash geek at Biogen. Carl Gutwin will be co-presenting with me. And so we are from Biogen. We actually work out of our Cambridge, Massachusetts office, our fair city. And for those of you who might not know Biogen, we are a biotechnology company. We focus on particular disease areas, hematologics, along with neurodegenerative disease. Sorry about that. My mistake. So thank you for bearing with us. We're excited to tell you about a journey that we've gone on this year for a program that we call Research Cloud. Now, Research Cloud is started about a year and a half ago. And we had a particular mission in mind with Research Cloud. We had a big driving use case on something that we launched in January of this year for joint collaboration with Columbia University. So Research Cloud's goal wasn't just this. We want to be able to collaborate much more than we do. But before we go into the details, I wanted to go over a little bit about genetics and genomics and NGS. So to introduce this, I do have a 2-minute oversimplified view of genetics and genomics. So how many people here work on genetics and genomics? So I'm going to butcher this. I apologize with everybody whose hands are up, but it's a fascinating topic. So if you're interested in this, I would recommend talking to everybody whose hands are up. So here's my 2-minute overview. Now, to start with, I do need my lab assistant, who is de-identified because this is reInvent and is being recorded. I also have my fully consented human sample played by Mr. Plato over here, and my Illumina HiSeq sequencer that we'll just say is played by the Plato Fun Factory. So, the first step is sequencing, and this is what a lot of people think about when they see genetics and genomics. So you think somehow you jam something in a sequencing machine and out spits the A's, G's, T's, and C's. Well, that's not exactly what happens. So somehow you do take your human sample, you stick them into your sequencer, you squish them through, and eventually you end up with stuff. Now, shockingly, this actually does represent what comes out of the machine a bit, because then you get to the alignment phase. Then you get to the alignment phase. So this is where the compute and the I/O starts. So what actually spits out of the machine, it's a more analog problem than it is digital. So you actually get strips of coverage of maybe A, could be G, across the genome. And what you do is you try to stitch them back together to come up with a confidence that you are actually looking at an A, G, T, or C. So in alignment phase, you'll hear people say we use BWA alignment. You take all these strips, you find your perfect human. HG19 is a reference genome. Maybe this is Khan from Star Trek. Maybe we don't want to know what this is. But after hours of processing, you end up with the double helix that we all know and love. But that's not all. I would say that this used to be 50% of your pipeline or more of it. Now it's less of it. So the next thing you do, oh, and by the way, when people talk about FASTQ files, it's really these strips on the ground. And when people talk about BAMs, that's pretty much your resulting genome representation. You're still not done, though. You've got downstream processing. And it's this downstream processing that when you go through it, kind of points out, this is the SNP for green eyes, and this is curly hair. And more importantly, this is what our researchers are looking for. This might be the diamond in the rough. So this is my butchering of genetics overview. Let's talk about evolutions in next-generation sequencing. So the slide on the left, the 1% to 2%ers, whole exome sequencing, RNA-seq, these are the sections of the genomes that are interesting in differences in humans. Now, if you see the right, that's the whole thing. So there's really a shift going on from whole exome analysis to whole genome analysis. And really what's going on is we've been able to do whole genome for a while, but we want to do way more whole genomes. And this, if you look at the file sizes with 24 to 72 hours of processing time, lots of pile-up, single file sizes of 800 gigabytes, this stuff is big. Actually, single file sizes of 100 gigabytes generally, total size is up to 800. Now, an example here is before we launched Research Cloud, we were challenging ourselves, what kind of network would we look like if we started doing more whole human genome analysis and we started collaborating with Columbia? So you see our current demand where we spike up over 1 gigabit a second, and then we just started running overlays, and we're quickly getting over 3 gigabits a second links. So network is definitely a driver, and we need a lot of it. Second part, security requirements. Genomes, they are us. So we want to make sure that we apply the most stringent security requirements to the solution that we're build that we can. So everything's encrypted, strong encryption at rest, strong encryption at flight, strong access controls on everything we put into Amazon. Private networks, VPCs, as much as we can throw at it. In order to enable us to do this at scale, we need to do it carefully. So this is Research Cloud. So we took these into the design requirements of Research Cloud, and these are our first 4 components of Research Cloud that lit up the beginning of this year, late winter. So the first component is, we obviously needed a big external network. So we actually joined Internet 2 at 10 gigabit levels. So we are definitely direct connected over Internet 2 from Biogen Cambridge today. We're going to go into details on exactly how we did that later on in this, because I know that's a big area of interest. The next thing we wanted something that looked like our internal HPC in the cloud. So we could take our existing traditional HPC, high-performance computing workloads, and put them at scale into Amazon. So we came up with Instant HPC, and we'll talk about that in detail a bit later. Now, the other 2 parts of this that we needed to launch with, we wanted to get a SaaS genetic pipeline vendor so we can run our production pipelines and also have the ability to do instant HPC workloads, so we have 2 vectors of attack on different problems. So we did choose, and we are lighting up and running on 7 bridges today. Finally, you need services. So services, we need people. And once you get this, you got to have the people to support it for the researchers. So we did actually launch a scientific computing group in Biogen to do this today. So because this is reInvent, enough of the overview. What I want to do is let's geek out a bit and deep dive into a couple of these components. So I'm going to turn it over to Carl, and we're going to go look at our research network. Thank you.
Thanks, Jason. So when designing the network component of our Research Cloud program, we had 3 main goals that we wanted to achieve. The first was to be able to support large data transfers between institutions that we collaborate with. So these data transfers, we're typically talking multiple terabytes, up to 10 terabytes or more per transfer. Our second goal was to support a private direct connect with AWS. This was mostly to enable high-performance computing with AWS, as well as access other AWS services. As a sort of a secondary portion to that, we wanted to be able to leverage other public cloud providers if the need arose. And the third major goal was to design this network to be 10 gigabit class end-to-end. We felt that 10 gigs was hit the sweet spot between cost of implementation and maintenance versus performance, file transfer rates, et cetera. So as Jason mentioned, we early on in the design process, we started partnering with Internet 2. And Internet 2 was actually a great partner with us to help the wide area connectivity portion of our design. This clicker is being a little finicky, I apologize. So for those of you who don't know, Internet 2 is a community research and education institutions. And they operate a 100 gigabit backbone that spans the continental US with lots of peering points between various institutions across the country. And since this is actually a tech talk, I'm throwing up a screenshot of the layer 2 console that Internet 2 provides. So Internet 2 provides a number of different services, among which we use the layer 2 and layer 3 services that they offer. And this is just an example of how you can actually use the Internet, use the layer 2 service to cross-connect different ports between routers within the network. Sorry, some glitches here. Okay. So with that, I'm actually going to dive a little bit deeper into the design of our network, go walk through it piece by piece. So we started off by completely redesigning our core on-premises network. This is not the entire network of Biogen. This is focused on the Research Cloud program that we're designing. We purchased a dedicated core router switch, which we connect to our high-performance storage, high-performance compute, as well as dedicated links from that core to instruments and workstations that are used by researchers that are part of this program. We purchased a dedicated firewall for this. This firewall is designed specifically to be able to handle the level of traffic that we intended to flow through this network. And the firewall protects us not only from our external entities, but also interprotects us with the corporate network. So we gain additional security between us, between Research Cloud and corporate. We've decided to follow the pattern of Science DMZ. And Science DMZ is, among many things, it involves the placement of a data transfer node in a special DMZ region attached to the firewall. This data transfer node is a dedicated physical node that's designed to deliver traffic or deliver files at 10 gigabits per second. So it has a sufficiently capable network connection and disk array. Attached to our edge router, we have a short 10 gigabit link to a 10 gig port on a router within Internet 2's cloud. This router is also in Cambridge, Mass. And from that router, we're able to gain access to the services that Internet 2 offers. So to the layer 3 service, that's our primary method of connection to our collaborating institutions, many of whom are also on the Internet 2's layer 3 service. As well, we're able to access Direct Connect over Internet 2's layer 2 service through a second 10 gigabit port that we've purchased from Internet 2's router in Virginia. So that router is located in a data center that Amazon also has Direct Connect presence in. So a short cross connect between that router port that we purchased from Internet 2 and the port that we've purchased from AWS gets us to our Direct Connect physical interface. And that Direct Connect physical interface is divided up among a number of virtual interfaces across our various accounts and VPCs. Again, since this is reInvent, I'm going to go over a little bit in a broad scope of our account and VPC structure. We've decided to go with the many accounts pattern of organizing our AWS usage. And this was for two primary reasons. First, from a security perspective, it's much easier to write our policies and our roles to be the level of fine-grained access that we're interested in. It also tends to limit the blast radius if we are ever in a compromising situation. And the other reason that was sort of a side benefit was it turns out with many accounts, our finance department finds it a lot easier to bill at the account level rather than at the tag resource level. So our accounts fall into three major categories. So we have administrative accounts, and right now we have really just two. A consolidated billing account, which is just dedicated for the purpose of running our consolidated billing, as well as a secure services account. This would host identity services and other things that need to be shared among the other various accounts that we have, as well as it hosts the Direct Connect physical interface. So that Direct Connect physical interface, as I said, is divided up among virtual interfaces. And those virtual interfaces are all in a class of accounts that we call private accounts. So they're private because they have access ultimately back to our on-premises network and our corporate network. And these are designed to be fairly locked down from the outside perspective. They have external internet gateways to provide access from those services direct out to the internet, so they don't have to go through our Direct Connect for internet access outbound, but they don't offer any services to the broader internet. And within those class of private accounts, we subdivide among the various business types. So we separate Comp Bio from Comp Chem as an example. We also separate among the traditional application tiers, prod, dev test. We also have a set of sandbox accounts that we let people sort of play around with and experiment with new features. The third major class of accounts are public accounts. So these accounts are designed expressly not to have access to our Direct Connect, because instead they're designed to offer services to the broader internet. So this would include like a collaboration service that we are designing, or if we're letting people play around with developing test websites in a sandbox sort of fashion. And where needed, if we need to provide services between public and private, we would use VPC peering. So I want to wrap up a little bit my section by talking about some of the things that we've learned as we've designed and scaled out this network to the 10 gigabit level. The first one, which sounds probably a little bit obvious to most of you, is you really have to find and eliminate the bottlenecks that arise or that are designed into your network. And some of these are, again, sort of obvious, like you don't have a gigabit network segment in your 10 gigabit network path. But some of them are a little bit less obvious. So, for example, if you're going to be doing bulk data transfers, you need to have a disk system that is able to, if you want to transfer data out at 10 gigabits per second, you have to have a disk system that's able to deliver data at 10 gigabits per second, or at least a gigabyte per second. And we were able to do this pretty reasonably with a modest-sized RAID array. But, for example, when you're doing your testing, don't do your testing from your boot volume, which is usually not scaled that way. Another thing is be careful with your firewall. So if you put a firewall into your network design and it has 10 gigabit interfaces on it, that doesn't necessarily mean that you can drive a single stream 10 gigs all the way through that firewall. Firewalls are designed mostly to handle lots of small streams rather than one gigantic stream. We were able to actually drive a large stream through our firewall, but it took a lot of tuning and testing with our security team, operations team, and with the developers of the firewall itself. And the last interesting bottleneck that I did not expect until we ran up against it was actually inside of EC2 VPC itself. So you might think that if you've purchased a 10 gigabit Direct Connect connection and you have a 10 gigabit capable EC2 interface, like a C3.8 extra large is one of our common, that you'd be able to flow 10 gigs between those two, but that's actually not the case. There are internal limits within the VPC structure that where inside of a VPC instance to instance you can go at basically the speed that the instance interface is. But if you're leaving that VPC, if you're either going inter AZ, well, actually it's not leaving VPC, apologize. If you're going inter AZ or if you're going out of the VPC, out your Direct Connect, there are smaller limits. So we were able to do about 1 or 2 gigabits per second on a per instance basis from that instance through our Direct Connect. Another major lesson learned, something that we had been warned about and we saw firsthand, is that packet loss combined with the types of latency that you typically see when you're going across the country really combine together to drastically lower your performance. So the folks at ESNet, they helped design high performance networks, did a test where they added packet loss into a network segment that was as small as 1 in 20,000 packets being dropped. And that combined with latency in the dozens of milliseconds range dropped their observed performance from about 6 or 8 gigabits down to a few hundred megabits. So it was a 17x drop. So you can see pretty drastic performance if you have even just small amounts of packet loss. So it's really important to design your network to basically not drop a packet unless there's an emergency situation. And the other thing that we noticed is to try and mitigate some of those effects, as well as effects that were caused by firewall issues and other things, is we really leveraged hard the technique of doing parallel stream transfers for bulk data transfers. Now, there are lots of technologies out there that'll do parallel streams. We've settled on the use of Globus Grid FTP for doing server-to-server transfers, and that tends to do a pretty decent job. But when we're going to S3, most of the native S3 tools don't support all of the features that we need in order to get the highest bandwidth possible, meaning multi-part, parallel upload, download, parallel files with KMS encryption. And so we actually had to write our own tool in Java using the AWS Java API to be able to get the best possible performance out of doing an S3 transfer. The last thing that we discovered was that, and again, we were sort of a little warned about this, was that it's not enough to just design your network and put it forward and say, oh, that's great, it's working, and walk away. You have to continuously monitor that network. That might be a little bit obvious, but you also have to continuously test the network to ensure that you continue to get the performance out of it that you had originally designed into it. Because you can keep track of packet counters, but if there's no active load on the network, you might not notice that something had just failed. So we use a tool called PerfSonar, which essentially conducts periodic iPerf tests between nodes, dedicated nodes within the network. And these tests are about 20 to 30 seconds, so they don't impact the normal functioning of the network. But what PerfSonar does is runs these tests, collects the results, stores them. You can browse through the website and get a graphical view of the actual performance of the network at a given point, and not just the current state of bandwidth on the network. So with that, I'm going to hand it back over to Jason, who's going to tell you more about our design and implementation of our Instant HPC tool.
Great. Thank you, Carl. So at this point, we have a really big network, and it is a luxury going from our scientific computing kit in Cambridge all the way to Amazon. So let's talk a little bit about what we do once we get there. So Instant HPC, we talked about how we wanted something that looked like a traditional HPC but ran on premise with all the security requirements that we were talking about earlier. So like I said, this time last year we were in final design going into implementation, and we were asking all sorts of crazy questions at reInvent last year because we were going through the decision process of exactly what this should look like. So our selections were, the first thing we needed to do is come up with an HPC framework. So when we came here last year, we had already started tinkering a bit with CFN Cluster. And we really liked what we saw. So we did decide to use CFN Cluster as our base for our Instant HPC. Reasons why we chose it. So number one, it is CloudFormation based. So some disadvantages, you're bound to AWS, but I would say that by the time you get done securing it, you will be bound anyways. The plus is you get all the abilities you would get with CloudFormation by going this way. So including, even last year when we were tinkering with this, it easily deploys in a VPC. If you've ever tried to get something like Star Cluster to deploy in a VPC, you know, it's possible you can do it, but it just worked. Other things that we got automatically, there's configurations in there to just encrypt EBS and ephemeral at rest. And the biggest reason we chose it is elasticity is based on auto-scaling and CloudWatch. So combined with CloudFormation, this makes elasticity great. It's native to Amazon, and we are definitely seeing this now, how well this elasticity works for us. And if you want more information, AWS and Amazon.com, HPC CFN Cluster, it is an open source framework. Dougal Ballantyne is here, and he's done a great job on it, and we definitely, more members of the community who are running on it would be great. Now, the second part to this is we need something that looks like a NAS. We need a shared file system that can support genetic load across the cluster. So we did choose Gluster for this. And the big reason we chose GlusterFS was encryption in flight. Encryption in flight and encryption at rest. We do get encryption in flight with Gluster. It's important to make sure everything's encrypted, and this is our big driving thing. These two put together are the base architectural decisions we had to make when we went into this. Now, I do want to deep dive into what we have a little bit, so let's spend some time on this slide. So what we've really done is we've used the base CFN cluster, where we get our VPCs, our key size configuration, we can get our ephemeral encryption through this, and we get a whole bunch of install hooks. Now, the other thing that we do is we have a whole bunch of chef recipes that fire on formation of this cluster. Base software installs, some security lockdown routines we actually have on a per node basis, installation of the Gluster software, creation of the bricks, and then we actually have a finalization that goes on right after everything's done that just turns it into our Gluster cluster. Now, I'm going to go into details about this. I'm going to go from left to right here. So the first thing we do is we start with a minimum size cluster. So let's just say it's 8 plus 1 plus the master's 9, C38XL for the purposes of this exercise. So we launch the minimum cluster. C38XLs, they have 2 SSDs on them. So we basically stripe the SSDs and then put Gluster bricks on top of each one. So then those bricks are ready to go. And that happens on instantiation of CFN cluster. One nice thing about CFN cluster, so we think it's a great thing, but you got to be careful of it when you start, is because it launches a CloudFormation stack, it all works or it all doesn't. You don't have partial launches. It'll totally roll back and wipe clean, which is great, but if you don't get your configs right when you first start with it, don't be surprised if you've got a couple rollbacks. So once you get through it, it's great, and we actually think that this is a big plus. So once it's there, the only thing we do, the Gluster bricks are ready, everything's ready to go. We actually do key management for the Gluster cluster on the master. And these keys are passed around, and they are, when we actually form the Gluster cluster on the bricks, this is what unlocks every node member. This also means that the cluster is completely disposable. If it's gone, it's gone. So next phase is that let's say this is 8 to 20 scalable, 8 nodes to 20. As load increases and the scheduler notices that there's a backlog, it will start launching extra nodes. These nodes do not participate in the actual Gluster disk component, but they do join and mount the Gluster cluster. So, as it lasts, we'll have more members of the cluster, and then actually as it shrinks, it'll go away. And it's great. It's pretty quick. I think the default is around 2 minutes when it notices, and it'll start launching 2 nodes at a time, and it'll keep doing that until you hit your max size or there's nothing there. As soon as it's gone, it'll shrink right back down, and we get back to our minimum size. Now, of course, this is all inside our security group, all inside our VPC, connected to our nice new Direct Connect over 10 gig level so we can shuttle stuff back and forth. And we actually do use encrypted S3 as the source system to move stuff on and off, and then when the cluster's done, it's done. Now, for an example, we have some base templates that we use. So this is NGS base 1. This is a smaller basic cluster. So this is 8 C38XLs, 16 cores, 2 by 320 SSDs. So our min cluster size is about 128 cores. We end up with a 5 terabyte Gluster cluster at $16 an hour. If it'll last to 20 nodes, we'll end up with 320 nodes or 320 cores, 12.5 terabyte ephemeral Gluster cluster, and $36 an hour. It shrinks, it expands, it shrinks. Life is good. And this is one of our basic clusters, and you'll see we have different templates. We have like a larger NGS cluster, and a computational chemistry cluster looks a lot different than this. But an important key to the way we think about this is we don't think about it as elasting our on-premise cluster and going really big in one cluster. We think about it as lots of individual clusters. So researchers can take their biggest experiments that might be clogging up the HPC, or it's a big thing that they've never been able to run, and we can tailor make an instant HPC for that researcher. And you can have multiple of these going on at the same time so they don't interfere with each other. So we don't think about the big bang. We do think about it as microarchitecture. These can get pretty big. And you saw from Carl's slides that they might be in different accounts, where computational chemistry will be getting built to the computational chemistry account. We might have a couple going for genetics and genomics. So also, because this is reInvent, we want to share some numbers. So this is a performance test, and it's actually a breakage test that we use when we're performance testing the system. Now, it's pretty basic. We just keep running the same BWA alignment job over and over and over on the same genome. It's pretty boring. The goal is to get it to go to its elastic maximum. And one of the things we were doing is, one, we were trying to break it, because we want to see how far we could go. And two, we were actually trying to figure out what the node ratios between the cluster nodes are and the elastic nodes. So things to think about: cores versus hyperthreads. So HPC people, how many people tune for hyperthreads? Cores? Yeah, so great debate over beer sometimes. So we have tuned for cores, which is why it's not 32. It's actually 16 cores, 32 hyperthreads. I/O intensity, right? So this is the big one. We built this for I/O intensity for genetics. If you're running a computational chemistry job, the I/O is very much lower, and the CPU is very much higher. There's also a configuration in CFN cluster while I'm here that you can actually have an EBS volume on the master. So, and you can encrypt that. You do get limited at 10 gigabits coming off the master, but that is a good configuration for specific workloads. But we were focusing on the high I/O workload. So we went through elastic ratios, versions. So we had to be very careful in the cluster version we went. We did go 3.7. That's pretty cutting edge. It got released right when we were launching this. We were feeding some stuff back through, but there were some performance increases and stability increases that we did see on our epigenetics loads, actually. So this is working. And then total disk needed, because you got to make sure that your cluster doesn't get big enough. So you can see that maybe you have to adjust your pipelines to start moving stuff to S3, or you can go with a 10 or 20 terabyte initial cluster launch. So what I wanted to show here was ratios. So essentially what we have is minimum time for that BWA alignment job, and then the maximum time, and then our average. So when we're at 1-to-1 ratio, you see that our standard deviation is at 9.8 seconds, which is perfect. That's what you want to see. Now, when you hit that 8 to 20, that ratio, about 2.5, you start seeing that your average is still pretty good. Your standard deviation is at $1.12. You do have a couple outliers. So this is about as far as we will elast the system as far as ratios go. We'll have a bigger base and then add more nodes. And then our stress test, so you'll see we'll go from 10 to 40 just to see what really happens. So you can see what happens is the standard deviations pick up. You get some big outliers, and your average times go up. The important part here is that it holds together. So the reason we wanted to show this is we spent a decent amount of time testing this. We probably spent a decent amount of money testing this, and we figured we could at least share. Now, I'm sure Stacy would love it if we just kept throwing compute, and Stacy and AWS would love it if we kept throwing compute at it and just were completely inefficient, but we are trying to find a balance, and we thought we would share. Another note here is that we don't use Spot because of security concerns. We have tested Spot a bit. It's exciting for a lot of the workloads, but because we are really locking down with security, we're avoiding Spot for now for these. So what this means is we can avert the question. So I used to talk about how, can I run 100 of those whole human genomes? Yeah, I can run 100 handful a month. Oh, and our storage is going to full, and you're going to break our network when we get it there. And when I used to show these slides internally at Biogen, I used to show this. It's like, yeah, $10,000. Eat your heart out. The most exciting part about where we are is we're starting to have these kind of conversations, where researchers can dream and do things that they haven't been able to do. When we can enable our researchers and they can do better research, it's the most exciting part of my job, actually. So, the team is important. This is a really big initiative. I want to thank the team a bit, and I'm just going to go through this, and we've got a lot of lessons learned, but just bear with me here for a second. So our scientific computing team, so Hank Wu, John Cody, Carl, and Rodney, who's a new member of our team that we're very excited about. Me and GDO, yay me. Our PMO, Kristen and Thomas Bolton. Bio team was a big part of what we did. They're an Amazon certified partner. Anushka on the genetics side, Chris on the network side, and Adam Kraut on the Instant HPC side. You know, our others are EVP, Andy Karabutis. I'm going to stop at Charles O'Donnell. He was our best use case in epigenetics. He was our pilot use case. He really killed our cluster. He had to bear with us, but he was finally able to do something he wanted to do, so that was pretty exciting. The rest of CompBio, Dougal, who has been working with us in lockstep to try to get this going for us, and also for CFN cluster. Stacy, our Amazon account rep, Dan Taylor, Brian down at Internet 2. And really important is notice how many people we have on the infrastructure and security slides. Our network team, our SecOps team, our security team, our infrastructure teams. We couldn't have done it without this big a team, and I wanted to thank the team and say thank you. So thanks to our partners for enabling our researchers to dream. Okay, so we actually had a lot of fun producing this particular slide, because when I used to show this slide inside of Biogen, it's like, how are we going to use it? You say, I don't know. It's pretty cool that we don't know. But we do know. We are starting to see trends on how we're using it. So number one, how we're using Instant HPC. Large-scale genetic reprocessing experiments of data sets that you can reprocess pipelines with newer technologies to get them in better shape so you can use them later. So that's one big use we're seeing of Instant HPC. Of course, computational chemistry. The computational chemists, they're going to use this. Just because we built it for genetics and genomics at high I/O levels does not mean that this doesn't work for computational chemistry. The templates are more CPU utilization and less disk I/O. Epigenetics, I mentioned that as well. They run some pretty crazy experiments themselves, so we are definitely using epigenetic workloads on this. Internet 2, how are we using that big pipe? So high-speed S3 transfers back and forth is something that Carl kind of did talk about a bit. Because this is reInvent, let's share. If you are doing some high-speed S3 transfers, we've got a base of 500 megs, part sizes, and 5 threads get you pretty well. But in order to get over 2 gigabit a second, we actually had to go up to 1 gig part sizes and 10 threads. And that seemed to be a pretty good sweet spot. We were getting over 2 gigabits a second, 2.5 gigabits a second to S3. Peered network tests. So one of the things about Internet 2, it's a big US network, but they're actually peered with other European research networks. So we are actually testing some of our downloads from places like Sanger and EBI through the network, and that's been pretty useful for us as well. Globus transfers, we definitely do Globus transfers, and doing that to collaborate with our different collaborators has been great. No more SneakerNet. No more disk shipping, although Snowball was pretty cool. I wish we had that last year. But no, this is great. Now, selfishly, I'm leading the data science and data wrangling teams. So we are looking at this usage of this in our data lake. So that's why we were focusing on S3 transfers at high speed. And we definitely want to use this to ingest. And we're learning from everybody here. We're piloting Redshift clusters. We've got on-premise Mongo clusters, and we are getting ready to start using EMR and use this fat Python. I'm pretty excited about that. So that's how we're using it today. Finally, let's go through some lessons learned. So I think the first lesson learned is if people asked us what we thought of CFN cluster and Internet 2, we'd give a big thumbs up. We're happy about those decisions. It's really enabling us, and we would definitely recommend that to anyone. Scaling and tuning. of course, you've seen Carl talk about what packet loss can do. You've seen how much effort we spent on just making our own copy utility to get the maximum benefit out of S3 transfers. The performance testing that we've done, I don't have to remind people in this room that scaling and tuning is really important. 10 gig's not always 10 gig. The aha moments around that were pretty funny. Like my favorite one, and Carl's like, duh, you need a disk that can support 10 gig or it ain't gonna go 10 gig, or even 1 gig for that matter, so that was pretty funny. So KMS and CloudFormation. So, we're pretty jazzed about CloudFormation. We're pretty jazzed about KMS. This is something that is evolving. So, in CloudFormation, you can definitely grab reference names to KMS keys, which we use a lot. But sometimes we want to use CloudFormation scripts to bootstrap a whole account. And we can't create the keys using that, so we do have a little syntactic sugar, because this would be awesome, really awesome if we could, but just know a lot of it's there, most of it's there. There's some gaps. EBS warm-up and launch time. So if you're going to use CFN cluster with the EBS configuration, we did kind of trip over a couple things. I think they're all fixed right now, but the first one is, you saw our instant HPC use case. Some of you might know that EBS, when you actually mount it, actually has a warm-up period where you have to kind of write blocks. We were seeing 20 to 30% hit on first write. But if you think about how we use that, that means we would take the hit and then shut it down and then do it again and then do it again. I believe it was just announced yesterday that that's gone, so that's pretty exciting. Number two, of course, when the new big EBS volumes came out, we had to try it, right? So we were starting to launch the bigger EBS volumes. When we did, there were some timing issues. They took just a little bit longer to launch, which actually caused some rollbacks. But I think combinations with changes to CFN cluster and some enhancements to the large EBS volumes, I think that's gone too. I have not tested them, but that's definitely something that we did walk into. Finally, everybody's got to talk about their aha, I can't believe you shot yourself moment, so I figured I'd share one. When we did, you saw our initial configuration, of course we naively thought that it was first in, last out on the compute fleet in CFN clusters. So when we launched our cluster, everything went great. When it elasted, everything went great. And then when it started shrinking, it started pulling out some of our core cluster nodes. And of course, the whole thing fell apart. So, and then we did it again because we had to figure out what happened because the whole thing fell apart. And then we figured out, yeah, duh. There are hooks that you can put in. So we do have hooks that basically say, if I'm not a core cluster node, then I don't go. So all these hooks are in CFN cluster. I just had to kind of share that. So yeah, so those are some of the lessons learned that we've had. Please remember your evaluations. And thank you for your time.